Last day we ended our discussion on the different steps that we can follow if we try to create a machine learning model using Keras API, right? And we took an example of ID's dataset to understand what exactly we are going to do. So I'm not going to repeat the steps anymore for today, definitely. So I hope you can remember the different set of functions that we are going to use, and the two most important functions during training is model.compile, which is for creating the settings of the model, and model.fit, which is used for training the model, to train the model. And once the model will get trained, we can either use model.evaluate function to evaluate the performance of the model, or we can directly use model.predict function to predict the on the unknown data set, right? So this is what uh, the the thing was. So what we can do now, like we can go to a Python code, and let's try to analyze the code line by line, and let's see how we are basically using the different functions over there. So as you can see here, this is a Python code which basically uses Keras library or Keras API, whatever you can say, to create a machine learning model and train that. Okay. So I have just written some, code with some very easy data set, which is an Irish one. And as you can see here, that there are some functions we are going to use, as I told you, that uh, say for example train test split. This function is very known to you now. You have seen that we use this function to basically to split the dataset into train and test data. And then the standard scalar function, which is again a part of scikit-learn package, we use for standardizing the data that we have. What is the reason of standardization? That already we have explained. I have explained last day in the last class. And this accuracy scores, this score is another function which can give you the accuracy of the data, I mean after training. Okay. So anyway, so in this part we don't have much intelligence regarding the machine learning model, at least, because it's this part is actually just loading the iris data, and just dividing the x and y part, like the input of the model and the target part, and then divide the whole thing into train and test set by train test split, and then standardizing the data. Okay. The main thing will start from here. So the first thing, I have written here model creation method 1. Why I'm saying this? Maybe definitely I'm going to show you model creation method 2 as well. So maybe we'll then easily correlate that what is the difference. The, okay, let me tell you, the difference is actually with respect to, you can say, the approach. The approach of creating the model. Okay. For example, as I told you that model is basically an object. But remember one thing, that we always, you know, create a model using sequential function that we have seen, right? So here you see I have called the sequential function, and I have passed the list of layers within the function itself. And this is the input in the sequential function. But here you see I have written tf.keras.sequential. I have not written directly sequential. Why? Because this sequential function is under Keras package, which is under TensorFlow. The TensorFlow I have renamed as TF. If you see here, you will see that I have written import TensorFlow as TF. Now, if you don't want to write in this way, you want to write directly sequential, in that case you have to import this sequential function directly over here. How you can do that? You can simply write from TensorFlow dot keras import sequential. If you write this, then you don't need to write tf.keras.pard because you have already imported sequential function from TensorFlow.keras package. So I hope this is clear to you. In the same way, also you see here I have written tf.keras.layers.dense. We don't need to write always in this way. Up to how much level you are importing depends on that. You have to write these dots because here, see, I have not even imported Keras. That's why when I'm writing Keras dot something, I have to write always tf dot Keras because last day I told you that Keras is actually on the top of TensorFlow package. The purpose of TensorFlow package is same, creating model, but the approach is different. The Keras actually makes easier for you, easier in the sense, easier with respect to writing the code. For example, if you want to create the multi-layer perceptron using TensorFlow package directly, then definitely you have to, you know, set, you have to use some function which is similar like sequential function in Keras. But writing or declaring the layers in Keras package is much bit easier with respect to writing code compared to TensorFlow package. So that's why we mostly use Keras, and there are a lot of other advantages as well. So we will discuss on that in future. But anyway, since you have not imported dense layer directly in the import part, that's why I need to write in this way. If you import dense directly from TensorFlow.keras.layers import dense, then automatically you can only write dense. You don't need to write explicitly write all these things. So it depends upon you. It's not that always you have to write this approach. First point. Now you see that within sequential function, as I told you, that the layers are presented in form of a component of a list. See, this is the component 1 of the list, then comma, then the component 2, then component 3. So there are 3, that means length of the list is 3, that means it is going to create basically 4 layers. Why I am saying 4? Because one layer is already, you can say, uh, by default, which is an input layer where we don't have any computation, right? And that input layer is actually the number of neurons present in the input layer will be defined by this input shape. Okay. And as you have seen that I have written here what should be the activation function of the layer, how many neurons will be there in the layer, something like that. So input shape is 4. Why? Because in my iris dataset, if you can recall, the total number of feature was 4. So naturally, you are going to feed 4 features at a time through your input layer. So you require 4 neurons in the input layer. And that's why it's given like this, which is nothing but input dimension, what you have seen last day. And these 4 input layers neuron will be connected with 64 first hidden layer neuron, which is created because of this first layer, first dense function. That 64 first layer of hidden neurons, hidden layer neuron, will be further connected with second hidden layer neuron, where the number of neuron will be 32, which is defined by this dense function. at the end, in the last layer, we will have three units, and also which will be connected directly with 32 neurons of the second inner layer. Now, question is why three? The three is that the reason is that I have, you know, just you can say that it's a classification problem, right? Classification of the IDs data where we have three classes. Since the number of classes is more than two, that's why many cases you will see that when the class becomes more than two and less than some finite value, which is say 3, 4, 5, 6, 10, or something like that, what we do, it's a class, right? So it's not a continuous value. So it's a classification problem. That's why we one hot encoded the target part. What I mean to say is that there is only one target, that is sure. So the class of the targets is either iris setosa or either iris virginica or maybe iris versicolor. So three classes, right? These three classes, if you one hot encode it, will be defined by, say for example, iris setosa will be defined by 100. Iris virginica will be defined by 010. Iris versicolor will be defined by 001, something like that. So based on the class where that particular pattern belong, one of the uh, target will be one and rather should be zero. So basically the target is defined with respect to a three component vector. That's why the output is given as 3. You may have your own explanation and you can define your own architecture accordingly. It's not that always you have to be 3. Okay. Now let's go to the next point. So in this way we have defined the model. Just the model means just the MLP model, that how many neurons will be there, how many layers will be there, and based on that automatically the weight matrix will be defined in behind. You don't need to do anything. And then the model.compile function will come, which we have given a very good big importance last day. And if you can recall, you see I have given here what should be the optimizer, what should be the loss function, and what the metrics basically we are going to utilize for understanding the performance of my model or training, during training. Now in general, since it is a multi-class classification problem, it's it has been seen that sparse categorical cross entropy loss function gives a uh, very good contribution on creating a good model. That's why we have used this. But it is not a, there is again I am saying there is no rule book that for this problem you have to use sparse categorical cross entropy. For this model you have to use mean square error or something like that. You can test with various loss functions, various optimizers, and whatever you will get best, which is accepted based on the accuracy or some other metrics, you can use that. So this is what the compilation of the model done, and then see I started training with the data set of the train, X train and Y train. X train is the input data in part of the train data, and Y train is the target of the train data. That you can easily understand, I'm sure. And here again comes this epoch, which I was saying last day, that how many times we will do the revise. So you can think in that way. So epoch means revise, doing the same training. I am giving the same training to the models with the same data. How many times? And then comes the batch size. So that means at a time, the error when the back propagation will start. The back propagation will start with some error value. So the batch size defines that how many error value will be accumulated at a time, and then back propagation started. So batch size 8 means once the first 8 value will be forwarded towards output, error will be calculated, then those 8 errors will be merged, and based on that error the backpropagation happened. After backpropagation weight will be updated, again next 8 input will go in the input of the model, will be forward passed, then again the um, error will be calculated, like merged, and so on and so forth. And here I have written variables equal to 1 just to show you what's actually happening during training. If you keep variables equal to 0, you will not able to see anything. That's the thing. And once the model fit done, I'm assuming that for my case 50 epoch is sufficient. Okay, maybe it is not sufficient for some complex dataset which we will see in future. But this iris dataset is very straightforward, and the three classes are very clearly separable with each other. That's why the 50 epoch is sufficient to create a best model which will give maybe 100% accuracy or something like that. So once the more training done, then we can easily, as I told you, model.evaluate to check the performance of the model, and see model.evaluate function take the test dataset, and it basically what it is doing, model.evaluate actually take the test dataset, test input, pass toward, I mean, through the model, the weight matrix updated, right? So it basically gives some predicted y. So based on the predicted y it has got and the test y that it already has, it basically calculate the accuracy and the loss, and that basically we printed as an accuracy here, something like that. Okay, and then maybe we can do some prediction using this model predict function on the same data. Maybe in future for real life scenario you will use some another data set for predicting whatever, and maybe we can see what are the classes, the predicted classes we have, and based on that we can have some accuracy score that we can calculate here with the test y, like actual y in the test data set, and the predicted y based on the test input. We get some accuracy score, and that basically I can print it here. So let's do one thing. Let's run this code. Okay, before go to the model creation method 2, let's run this code. So I'll just simply run this. Then I will run this particular line, and then this line will start. So once I will click run, you will see it started running, and see epoch 1 2 3. The number of data is very slow, very small. That's why it is showing, you see, epoch 20 out of 50, 22 out of 50, epoch 23 out of 50. In this way it is running. Now questions come. One thing that you see, for every epoch, if you look into very carefully, see, for every epoch it is representing 15 out of 15. What is this? What is this? Why 15 comes? In epoch 1 it is 15, something, 15 amount of something is there. In epoch 2 also 15 is there. In epoch 3 15 out of 15. Epoch 4 15 out of 15. What is 15? If you see, if you try to find out the significance of this value 15, it's actually very easy. Let me just try to make it clear for you. See how many data set we have in the in the original data set. Total number of data, I mean total number of pattern available in the iris data set is 150. Okay, see here you have chosen trend test split by test size 0.2. That means 80% will be on train data, 20% will be used for test data. So if you divide 150 rows by 80-20 ratio in the train data, you will get 120 rows, right? 80% of 150 is 120, right? Fine. Now if you see, come to this model dot fit part. When we are fitting the train data in the model, we are specifying that I want to use batch size 8. That means this 120 train data will be passed in 8 batches. So if you see how not 8 batches, sorry, will be passed into batches of size 8. So if the size of the batch is 8, then how many batch will be there? 120 by 8, which is equal to 15. That means it is basically representing, since the model, the whole processing is very fast, that's why you are not able to see the changes here, but actually it is not, it's actually the last output, which is, you can see it started with 1 out of 15, then 2 out of 15, 3 out of 15. In this way it ended up to 15 out of 15. So 1 out of 15 done means first 8 batch completed. I mean first batch completed, first batch of 8 data, because every batch contain 8 data point. Then 2 out of 15 means the next batch is going, is continuation, is actually is in under training. 3 out of 15 means the next batch. So every batch means 8 point. So that's why 15 out of 15 comes. If you change the batch size, you will see it will change. For example, if you change the batch size to 15, then what will happen? That means you want to pass 15 data point at a time. You want to calculate the error of 15 data points. Based on that, you want to backpropagate it. So if the batch size is 15, number of batch will be 120 by 15, which is 8. In that case, you will see it will show 8 out of 8 at the end actually. So let me just run the model again, and maybe it will, you will see it's like this. See, here now it's come 8 out of 8, and this is the reason. Since the data set is very small here, so it's doing so fast. But maybe in future, when we will work with a lot of data, maybe 10,000 or 50,000 data points, then the number of data point in a batch will also be in terms of thousand. So maybe in that case, sometimes we use batch size of, say for example, 512 data point, 1024 data point, or 5000 data point in a batch size. Depends upon the total size of the data. Anyway, so I hope this is clear. Now you see here it is showing that how many times it has taken, that's fine. And also it is representing that in this first epoch, what is the loss and what is the accuracy. As I told you that the model, the data set is actually very clearly separable. That's why from the very beginning, the accuracy is 0.97. But in some other complex data set, maybe you will see the accuracy will start from 50% and it will gradually go up to 90% or something like that. Okay, so you see here the loss, if you see, it started with 0.0574. It gradually decreases. You see, it gradually decreases and sometimes also increases. But if you just print the loss, I have not printed the loss here, but you see, if you print the loss, you will see it's a pattern of, going downwards. See, it started from 0.0574, somewhere 0.04, 0.04, and then it gradually downs and becomes 0.03. So definitely I can say, and at the end basically it is showing 0. Okay, this is for testing. So up to at the 50th epoch, the last revised time, the loss is basically 0.0360. So which is basically very, very less than the first loss. So if you just try to, do a line plot of the loss values, you will see it's a bit, you can say, monotonously decreasing loss, right? And that is basically expected, right? So as a result, in the test dataset, it is showing test accuracy 1.00. It means basically it is giving 100% accurate data. So every data point is accurately classified in the test dataset. It's not 1%. It's 1.00 means actually it's a point. So if you just try to make it in percentage, it will be multiplied by 100. Just like here, accuracy 0.99. It means actually 99.17% accurate. So this is one form of thing, like but you see, the method 1 and method 2 that I have divided not with respect to the fit and compile part, but mostly you can say with respect to the coding style of declaring the model and all. So let's see, there is no such difference with respect to learning. Okay, so if you see here, if I go to the model creation method 2, see here the way of defining the model is bit different. You see, I have initially defined model equal to tf.keras.sequential. I have not passed anything here. It's simply like a creating an object of sequential class. Now one by one we have added the layers. For example, this is added of the input layer. Input layer is important. Since this is input layer, that's why you see I have not specified any activation function or something like that. I have to specify what should be the shape based on the number of feature in my dataset. That's all. Once the input layer defined, then we have to start the defining hidden layers and as well as the output layers. But for both hidden and output layers, I have to specify the number of neurons, the activation functions, as well as maybe some other things if I want. That's why there is a clear difference, I hope you can see, with respect to defining the layer for input and defining the layers for others like hiddens and the outputs. And then the rest of the thing is basically same. I have not changed anything over there. So my intention not to show you that how different trainings were doing. My intention was to show you what are the different way of creating a layer. So you can use this approach or you can use some approach something like this. Anything is acceptable. It has to be just logically correct. That's all. So there is no specific direction that exactly this code you have to use in this way like that. Okay. But let's do one thing. Let's do it verb was equal to 2 here. Okay. If I do this, then and if I run the code again here, see what will happen. It's now in verb was equal to 2. See, um, it is also showing the number of times it is pending for every epoch in verb was equal to 2. But see, as a programmer, when you will create a model or you will basically try to train a model, maybe you will be interested to see that how good the loss is decreasing and how accuracy is increasing, right? So only these two is sufficient. You don't need to check every time that what exact millisecond or microsecond is it is pending for every epoch like that. So, to some extent, you can say as a programmer, I feel that var was equal to 1 or var was equal to 2 is almost similar for your purpose. Because your purpose is to check mostly these two things, which is available in var was equal to 1 as well as available in var was equal to 2. But if you put var was equal to 0 and if you run the code, see you are not cannot see any roco, any output. You are directly see one by one, which is nothing but this part is for the test data, not the train. So the test data you cannot see. That is what the var was equal to 0 intention. that you don't want to check that the intermediate performance during training. Then only you can put var was equal to 0. But in general, mostly we use var was equal to 1 because we mostly interested to see that how good the model is actually, and the accuracy is increasing or the loss is decreasing. So this is all about a very basic understanding of how you can use a Keras model, or sorry, a Keras API or a Keras library for creating a multi-layer perceptron model. But you see, remember, Keras is not for only MLP models. Keras is actually for other machine learning models as well. Okay, but since we are going forward, we will do something more after this. That's why I'm just showing you with respect to our creation multi-layer perceptron model. And also you will see in future that we will, when we will start learning deep learning, we will try to create models for different complex data sets. At that time also these Keras will be very useful for you. So be very prepared and be very you can say habituated of using these different functions and different parameters. So I will always suggest you to write code yourself, because see here you don't need to write the backpropagation from scratch. So the maybe you can say that your 90% of job is done by Keras itself. You just need to you know create the layers perfectly and also call the functions perfectly. That is the only your job. Okay, so you must have a good practice on this so that you can use this in future. So we can stop the understanding the Keras model here. Maybe we can explore in future. So now let's do one thing, but one thing is still missing here, that we have different type of settings possible. Like we have optimizers, or not but other optimizers available, different loss functions available. Even I have not even included here the learning rate. The learning rate is decided by the model itself. But if I want to control this, that is also possible. Now see, that means say you have more than 2 3 parameters, which is very vital for your model training. And for every parameters you have different options. Like optimizer parameter has different option, loss parameter has different option, metric parameter have different option, learning rate may have different option, and many more like this. Now how you will understand that which particular combination of these parameters will be the best for your model? That means you have to run the model with all these different parameters one by one, right? So in that case, manually, what is the option? You will change this option, the parameter name manually, which is very inefficient job, because the options, if the option increases, it will be difficult to track that. In that case, basically what the things that basically we do, that is what basically we call hyperparameter tuning, which basically gives you a way of, it means tuning of hyperparameters. What is hyperparameter? All the different dependencies that we have in this model are all basically hyperparameters. The hyperparameter can be this optimizer name, the loss function, the metrics, the learning rate, the number of neurons in your layers. All these are hyperparameters. So this tuning this hyperparameter is extremely vital when you will work with very complex model. How to do this? So let's do one thing. Let's go back to the slide again. Let's see what exactly hyperparameter tuning is, and then we will see how we can implement this hyperparameter tuning using Keras again.